Okay, so today, what I want to talk about is repeated measures designs. A couple of different ones, but they're all sort of a spin on the same thing. Let's say you're interested in learning or forgetting, which are pretty common things we're interested in psychology, right? Really just change over time. Independent groups won't do here. Like we would normally I've talked about this, how this is an important assumption of analysis of variance, is independence of events, of observations. But I can't use independent events when I'm looking at learning, can I? I have to look at your change over time, and your score at time 2 is dependent on your score at time 1 because it's always you. I'm sorry, I'm taking it. You're standing sitting there. I have to look at you over time. Or if I was doing forgetting. So I give you a list of words, and then you try to recall them, and I have to look at your performance at 1 hour, 24 hours, whatever. Could you do it separately? You probably can for forgetting. I don't see how you do it for learning, really. You don't want independent groups in these cases. What you're looking for are not independent groups. You actually want to test the same people over and over again. Right? So when I'm assessing your skill in a class, I look at your tests over, I can look at you one time, another, etc. So we're looking really at change over time generally, which is a pretty common thing in life sciences in general, not just psychology. So it's also true in biology, where we look at change over time. Okay. So you get something like this. If we had our retention interval, we were talking about retention interval always, we're talking about memory over time. So our retention intervals of 5 minutes, 1 hour, and 24 hours, and you have the same group 1, group 1, group 1. Okay, so it's the same people tested over and over again. It's the same people tested over and over again. Okay. So there is a potential problem here, and that's that, as I mentioned at the beginning, the observations are not independent, are they? And independence of observations is the one I keep saying, independence of observations is the assumption that I keep saying, this is the one we can't violate. We can mess around with random sampling. We can mess around with random populations. We can mess around with all kinds of things. Variance, homogeneity of variance. We can't really mess around with independence of observations because the model doesn't have that in it. It doesn't have the model, x equals mu plus tau plus epsilon or whatever model you're using. It doesn't have dependent observations in it. Let's put that in the model. Just throw it in the model. Right? All these assumptions, like half the assumptions that are half follow the F test, really fall out of the model. So let's just change the model. Nobody said we couldn't do that. Let's do that. So our model's going to change. Now it looks like this. It's x equals mu plus tau plus pi plus epsilon. Now again, here pi does not mean 3.1415927. It sort of stands for people. I always think of it that way. So any score equals the grand mean plus the treatment effect plus error. You've seen all that before. And then there's an effect of subjects or an effect of people or participants, whatever you want to call it. I'm going to say subject, but whatever. Okay, so that's the effect of subjects. We're just going to throw that in the model then. Questions so far? Good. Very warm. It's amazing how warm I get when I do this. Take my mask off and I pick up the shirt. So that's the model. What happens with that model? Well, we have a design that looks like this. So that's subject 1, subject 2, subject 3, subject 4. So we have 4 subjects we're testing 3 times. It could be simply 3 subjects we're testing 3 times. Then if I pick 4 because it's easy to draw. So we have, what we've done is we've decreased error. We've decreased error. Now, why do I know we've decreased error? Up for a sec. I should be able to just kill one of these projectors. Actually, instead of doing that, let's do that. So, yeah, maybe not do that. Yeah, let's not do that. Instead, I'll kill one of the projectors. So. Okay, good. So we'll just kill this projector for a sec so I can write some stuff. So our original model, when you think about a vanilla, if you want to call it that, analysis of variance, is this. It's not that. It's the garbage. Let's get a different marker. There's a good one. Right, that's our old model, x equals mu plus tau plus epsilon. Our new model is this, x equals mu plus tau plus pi plus epsilon. There's only one place this pi thing can come from. Tau is already here. Of course, grand mean's already here. It's got to come from here. So we're partitioning the sources of variation further. We're partitioning the error into 2 different things. We're partitioning it now into pi and epsilon. So it's now partitioned into pi and epsilon. Does that make sense? Remember, the numbers don't know where they come from, so you can do this. So while you're thinking, wait, what do you mean you get the same people? Yeah, I know that, but the numbers don't know that. Second. But what we've got, we're wondering about is we've paid for our decrease in error, because we've obviously made this thing smaller if we split it into two parts. But we pay for this in degrees of freedom. So a standard, and that's what we have on the left, way of analyzing a design like this would be 2 degrees of freedom for retention interval, because we had 3 levels. 9 degrees of freedom for, well, 12 all told observations, 11 degrees of freedom, so we end up with 9, which is also big N minus K. Big N was 12, we subtract K, there are 3 groups. That's 11. I'm sorry. What am I saying? Yeah, it is 9, not 11. However, if we do this, we now have retention interval. Does that come back on? We have retention interval as a factor. We have errors still. We have total still. We have subjects now as a factor. I said last week that we can view subjects as a factor. The numbers don't know where they come from. So there can be a Dave level of human and an Evan level of human. Those just are things. The numbers don't know that. We're going to consider humans or subjects, we're going to consider that as a random factor because it's not really a fixed factor, it's closer to a random factor. Okay, I think I turned it on. Does that make sense? Questions about that? So that's what we've done here. So we've made error smaller, but we're paying for that in loss of degrees of freedom. because we're going to end up doing a test with error, but this time now error has 6 degrees of freedom. Has 6 degrees of freedom instead of 9 degrees of freedom. And if you take a look at an F table, you'll find that the bigger the degrees of freedom, the smaller the number, the smaller the F you have to exceed. So we've made it a little harder to exceed a value because we've made that value bigger, because the degrees of freedom are smaller. But we've made the denominator of the fraction smaller, which makes our F bigger. There's no free lunch. So you got something good, partitioned error, but you now have to exceed a bigger critical value. The next assignment, which I believe I posted, assignment 3, actually literally asks you, has it made sense to do this kind of analysis? Any design has a finite amount of variation. The numbers vary from the grand mean. That's all that is. And it therefore also has a finite number of degrees of freedom. And that's the number of observations minus 1. And then we split that all up. So we partition sums of squares, we partition variation, and we also partition the degrees of freedom that go with those variances. Okay. So all we've done here is we've partitioned the degrees of freedom and variation a little further. So the mean square for treatment is actually going to be the same in this if we did a repeated measures analysis of variance, or we just did a plain old sort of vanilla one-way analysis of variance. So mean squared for retention interval, we'll call it in this case, instead of mean squared for treatment, will be the same. It's going to be the same in both analyses. It's the same in both analyses. The question then is the reduction in mean squared error with the loss in degrees of freedom for error? And as I said, I believe literally that's one of the questions on the next assignment. Any questions up to this point? I can answer. Happy to answer them. Okay. Okay then. And it's almost always, by the way, the answer is almost always yes. Now and then, I could see it working that it wouldn't be, but it's almost always going to be worth it. It's almost always going to be worth it. Now let's think about this for a sec. Is it realistic to think that x equals mu plus tau plus pi plus epsilon? Is it a reasonable assumption that this describes the design, that this describes the variation, that it's grand mean plus treatment effect plus the effect of subjects plus error? Or is that overly simplistic? And I think, considering what I did, why we would stop now if it wasn't overly simplistic. So it's a little bit simplistic. Really, pi should interact with tau. And here's the way we think about this. Let's say we're doing a memory experiment. Again, we'll be forgetting. And some people have poorer memories than other people, which is the way it is. Everybody generally goes down over time, over attention. But some people go down more than others. Wait, that's an interaction. The effect of treatment depends upon the person. That's an interaction, isn't it? Right? So if Evan's memory is better than my memory, we look at his curve, it's like this. We look at my curve, it's like that. Everybody's going to go down. But if I go down more quickly because I'm older, I'm old. That's me. If that's the case, then we really should have an interaction term. So in fact, it should be tau pi. This starts to sound like something about a fraternity. So happy we don't have fraternities here. Just saying. So it's really much more sensible to assume that there's an interaction between tau and pi. This actually isn't going to change calculations of any sort. But it gives us a basis for how we're going to actually analyze how we're going to do the f-test. So our model actually changes subtly. Now our model is x equals mu plus tau plus pi plus tau pi. Ever had that tau pi? It's delicious. Thank you. Nothing like a pie joke. Okay. Oops. So here it is again, x equals mu plus tau pi plus tau pi. Wait, Dave, there's no epsilon? There's no error? Yeah, there's no error. There's an error term. There's something we're going to divide by. But there's nothing left over. When we have the model like this, we've exhausted all the degrees of freedom. So let's say, again, we had, was it 3 levels of the independent variable, so 3 levels of, 3 levels of tau, and 4 people. That's going to be 2 degrees of freedom, 3 degrees of freedom, 6. 2 and 3 is 5 and 6 is 11. There's only 12 degrees of freedom. There's nothing left. Yeah.
Oh, I kind of answered the question in the process of your
Okay. I was sort of thinking that was what was going to happen. Yeah. So we've exhausted the degrees of freedom. There's nothing left over. It doesn't mean there's no error term. You can probably guess the error term is going to be this guy here, tau times pi. We have an error term. It's just not left over. We reserve epsilon for leftover stuff. We now know where all the variance comes from. There's nothing left over that we can't assign a name to, so we call it error. So what we're doing is we're treating S, so that's subject, like a variable. We're treating it just like any other independent variable. So in fact, the design looks like this in this case: retention interval, subjects, retention interval by subjects, and total, 2, 3, 6, 11. As you can see, there's nothing left. There's no thing we can put left that says an error or residual or whatever. There's only 11 degrees of freedom all told in the design that we have, that I had up on the screen, and we've exhausted all the degrees of freedom. It adds up to 11. There's nothing left. You can't have something with 0 degrees of freedom. So we've exhausted degrees of freedom. I think I just moved this, unfortunately. The downside of using this as a remote. How does this work? Our error term is actually a treatment by subject interaction, as I said. So subjects are a random factor. Oh, remember I told you all about expected values in mixed models, and you were wondering why would you tell me this? Well, this is one. This is one. It's because to find out what we divide by, we have to look at the expected values. And we can do that right here. And subjects are a random factor. The expected values work out. I'll show you that in a second. Remember I said, oh, don't worry, nobody ever does that. You never have mixed models. Well, whenever we have subjects in here, we actually use a mixed model. Nobody has mixed models typically, or random effects models when they're using regular independent variables. But as soon as you start using repeated measures, and you think of subjects as a factor, then we actually have a exponent. We don't test the subject factor. There's not going to be an error term for it, which I'll show you in just a sec here. So we're never going to divide mean squared for subjects by anything, right? So if we take a quick look back here, let's go back a slide. Maybe go back 2 slides. No. Where is it? There it is. Yeah. So we have a subjects. There's the degrees of freedom. There also would be a mean squared or sum of squares. A sum of squares mean squared. But we don't test the subject factor. We test the retention interval factor. That's what we're interested in. But we don't test the subject factor. Keep going back to where we were. So we don't test the subject factor. So you mean we just leave it there? Yes. We can't test mean squared for subjects. There's no error term with the right expected value of the mean squared. Also, who cares? What groundbreaking thing would it be if we found the main effect of subjects? Your big paper you're going to get in Nature or Science would say this: people are different from each other. It's not really a publishable result. We kind of knew that. Thank you. So we can't test it. It's statistically impossible. I'll show you why in just a sec on the board. But it's also, it doesn't matter. I know it's sort of, I remember when I first learned about this stuff, I thought, but it's right there. But it doesn't matter. You can't test this. It's not a thing. And it doesn't matter even if you could test it. Because the big result would be you found people are different from each other. Well, call the people in Stockholm. It's time for your Nobel Prize. People are different from each other. That's not really a result. And the reason we can't, let's see if I can do that. Yeah, I can just do it here. So the expected values of the mean squares, because that's how we always figure out what to divide by what, right? The expected value of mean squared treatment, the expected value of mean squared for subjects, and the expected value for the treatment by subject interaction. Now this is a mixed design, right? Because the treatment is fixed and the subjects are random. So the effect for treatment is going to be treatment plus the interaction. The effect for the interaction is going to be the treatment by subject interaction. And the mean squared error, or the expected value for the mean squared for subjects is pi. Now if you remember, if we go back to alphas and betas with an a 2x2 kind of design, a two-factor factorial and ones between, ones within, we'd have epsilon at the end of these, but we don't have any epsilon term. So that's pretty easy. Look, we isolate treatment, mean squared treatment, we would divide this quantity here, mean squared treatment by subject interaction, because this cancels this, so we end up with treatment on its own. And we have nothing to divide that by. It's just sitting there on its own. So it just mathematically can't be done. It's not just that we don't care. Even if we did care, there's nothing we can do. Even if we thought it was something we would want to test, and again, if you're at all like me, and I hope you're not, because the world needs fewer people like me, not more. But if you're at all like I am, it bothers you seeing something sitting there and you're not going, well, what about that? Shouldn't bother you. There's two reasons. You can't test it, and it doesn't matter. Does that make sense? So it's mathematically impossible, and it doesn't matter anyway. All right. So that's what's called a simple repeated measures design, repeated measures analysis variance. Let's make it a little more complicated. Remember the matched pairs and / correlated t-test, the one where you have before and after the same subjects, so you match subjects on a factor. But that's a thing we talked about earlier on. I talked about that from the comfort of my podcasting studio to you over Zoom. So it's before and like I just said here. Matched pairs, same sort of deal. Subjects usually matched on the dependent variable. So if I'm measuring heart, in fact, the example I used when I talked about that was looking at the effectiveness of a blood pressure medication, and we would probably match subjects on their blood pressure. So let's say our blood pressure is matched, which it probably doesn't. By the way, this is the calm version of me. You should have seen me before therapy. Think I'm intense now? It's so different. My wife's the same. So, let's say we match them. You get the drug, I don't get the drug. You consider us the same subject, sort of, because our blood pressures in this case match, which give you probably. No, mine's fine. Actually, a little low. I was surprised. When your blood is basically thinned by the amount of gene I drink, it really helps your blood pressure. So we match subjects in the dependent variable. So by extension, we should be able to do this analysis of variance. Instead of having two subjects, maybe we find 3 or 4 that match on something. So we're going to do the same thing with repeated measures analysis of variance, but instead of matching individual subjects, we're going to have, or 2 subjects, we're going to have 3 or 4 subjects, and we're going to put them in what's called a block. What we need is something called homogeneity of experimental units. We're all experimental units. And if we 3 match up on our blood pressure, we would be homogeneous on the thing we're interested in. That would be homogeneity of experimental units. I remember when I keep talking about when they changed the name from subjects to participants a long time ago, admittedly. I remember saying, you think subjects is bad, what do you think about experimental units? Let's start using that. So we say in statistics, you can't really call your participants experimental units. Maybe like your honors thesis. That would be a little weird. So there's a few ways we can do this. Matched pairs or matched groups, like we were talking about here. Litter mates or twins. So I've always found it interesting to think if you just take a quick step back and realize that human twins are a litter of 2 humans. It's weird, right? So your mother had a litter of 2 instead of 1. You would do this a lot. You might do this with some sort of. There's a lot of developmental experiments you would do this with, and let's say you've got litters of rats. So now you know that they're in vivo, in utero. The environment was exactly the same because they were all inside the same mother rat, same dame rat. Okay. Oops, I think I moved this again. I did. do is we block. Again, if it's our blood pressure, we're going to block on that variable. It's called we block on. We're just blocking it. And it's what we would consider maybe a nuisance variable. A nuisance variable is just one that gets in the way, but we can measure it. It's variance that will. This wasn't accounted for. We just make error bigger, but we can account for it. We can measure it, and then we block on that variable. This now reduces error, because remember, the only place that you can take error from, or take variance from, is error, is epsilon. It's going to give us greater power, because the smaller error is, the smaller the denominator of the fraction is. The f fraction, the f ratio. The bigger the final f value is. The structural model is pretty much the same. And in fact, it turns out that while I talked about repeated measures first, because I think it's easier to get your head around, repeated measures is a special case of the randomized block design. So here's the structural model. Oh, this is actually going to look familiar. This is what we started out with. And like I said, this is the general case. The special case is the repeated measures. So in our case here, we have any score equals the grand mean plus the treatment effect plus the block effect plus error or residual. So in the special case, when you have actual repeated measures of the same subject, you throw interaction in there. We're not going to do that with the randomized block. Because with the randomized block, because we have homogeneity of experimental units, we assume that there's no interaction at all. Here's our assumptions. The sum of the treatment effect should equal 0. That shouldn't surprise you. Then we have two random variables, not just one. We have two random variables. One of them is error, which should be normally distributed and independent with a mean of 0 and a variance of sigma squared sub epsilon. And then we have the effect of the block here. The block effect should be normal and independent with a mean of 0 and a variance of sigma squared sub pi. Good. I'm going to give you an example of a design like this in a second. I think you'll see what I'm talking about. I know thinking about these randomized blocks is a little bit weird because repeated measures is okay. You can think about forgetting or learning. This is a little more complicated. I'll give you an example in just a sec. Oh, and error is independent of block. So the amount of error, if your one block is the same in us, well, not the same. It doesn't matter. It can be like this and this block and this one. We can't predict how much error you have by which block you're in. It's independent. There are no interactions also between tau and pi, as you can see back with the model. So what this is saying is each block is affected the same way by the independent variable. That's a pretty big assumption because there's nothing there that allows us to test it. So it better be true or error is going to get big. Better be true or error is going to get pretty big. Because the only place unaccounted for variance can go is into the error terms, into epsilon. Now, if there's an interaction, it just says that here, well, then epsilon will increase. You know, I've taught this stuff so many times, I think I can do it without the slides. I'm just going to have to talk. Get light. So you lose power. Now the nice thing is if you lose power, that means you make more, your test gets more conservative. So you're less likely to find something that's really there, but you're not going to say something's there that isn't there. If your test gets more conservative, at least you just blew finding something. You don't end up saying, okay, so there's psychics. Like, you can't say something stupid. You don't have false positives, you get more false negatives. Is all. That's actually okay. As far as results go in science, we would want more false negatives than false positives. Science tends to be conservative, and it's for a good reason, the whole way knowledge progresses. Nothing wrong with it. So how do you fix this? Don't have interactions. And you can't find, the only way to find out if there's interactions would be to look at a graph after you collected the data and say, do those lines look like they're crossing at all? Like, you can't actually test for it. So here's an example. We have, and the example I'm using here is, that I've made up, is the idea of learning a language. Okay? And it's based on 3 different teaching methods. Now you would think, comparing language learning, that would be a sensible thing to test. There's different methods. We can do a straight up regular university lecture type approach. We'll call that method 1. Method 2 could be an asynchronous, we've all done these recently, an asynchronous class approach where you watch materials or do it at your own speed. And let's call method 3 an intensive approach that involves doing nothing other than that class. So for 3 weeks, all you do is take that class. You do it for 6 hours a day. You do the same amount of instruction time as you would in a regular class, except you do it all in 3 weeks. Which is a teaching approach called a block approach that we thought about adopting in 2011, but we were afraid of it. I wish to hell we would have done it, but that's a whole different thing. It's got other places where you take nothing but one class for 3 weeks. You take it all day, that's all you do. But you know what, if you're taking only one class, you know what that would allow you to do? Like, for example, if we were teaching history of psychology, we could all save up money all the way through 4 years, and then in your 4th year of history of psychology, we'd go to freaking Germany, where psychology was going, and we have the class there. But no, let's not have that. Anyway. I'm still a little bitter because I really wanted to do that. You know, you would think maybe if we're learning a language, previous experience with the language, and my wife teaches French, and she would tell you that right away, that your previous experience with the language really has an effect on how good you are in a course. She has people in her class, her French communication class, for example, that come in and they really have taken nothing but just basically core French. That's like up to grade 12 French, and some of them haven't even done that. Which is tough because that course is all taught in French. So there's the low level. And then medium, there are people who have done things like taken French immersion. Right? So there's French immersion schools. And then finally, there are people who are just bilingual people. Right? There are people like her, for example. My grandfather, another one like that. Prime Minister. You know, people just go switch back and forth. You would think that previous experience would affect how you did in a class. It does, like I said, as you would imagine. So we can block people. Oh my God, is my leg bad? Almost exactly 2 years ago today, I broke my leg, and it still hurts, and it really hurts today. Anyway. So this is a low, medium, and high. We would block on that variable. It's a nuisance variable. We can imagine it would be an effect of your previous experience with the language, regardless of the teaching method. And we could suck that variance out. So that's what we're blocking on. And then we can look at these and see if they're different from each other with analysis of variance. Now you look at this and you say, well, Dave, you said there should be no interactions. It looks to me like there's an interaction there. It does. My take on this is usually if it's an ordinal interaction, so the lines don't ever cross, you're fine. All it's going to do is make error a little bit bigger, but you're fine. If the lines cross, you should just literally do a different kind of analysis. You can't use randomized block, you use a different kind of analysis. Okay? Questions about that? Now we could have more than one, we could have more than one variable. Why not have this experiment here, which is literally a classic kind of experiment you do. You do implicit and explicit memory tests, and you do 3 retention intervals, 5 minutes, 1 hour, 24 hours. And it's the same group of subjects, group 1, all the way through. So, what's the model here? It's x equals mu plus alpha plus beta. So it's just A and B. They're just retention interval and memory test type are just regular variables. A and B, alpha, beta. Then we got pi. That's going to be for subjects. Alpha pi, beta pi, alpha, beta pi, and there's no epsilon because we exhausted the reason. There's a lot of terms here. Right? And now that you know that a lot of times you're dividing by interactions with pi, there's a lot of possible error terms here. So what do we test with what? Well, one thing we could do, which we will not be doing, is determine what all the expected values of the mean squares are. If you want to do that, you go nuts. I don't want to do that. I'm going to show you a way to do it that doesn't involve having to calculate expected values of the mean squares. In my stats book, when I was in grad school, at the back of the book, there was a whole section on determining expected values of mean squares for different designs. And it's like, this is a nightmare. And then I was taught this really simple method to figure out what you test with what. And it works like this. The first thing you do is you list your subjects. And I'm just assuming there's 10 subjects per group. So subjects. And they have 10 minus 1 or 9 degrees of freedom. Then retention interval. So now subjects and then your effects themselves. We have 3 different retention intervals, so we have 3 minus 2, 1 degree of freedom. And then we take retention interval and cross it with subjects. So this with this, and we get that. Now, next we list M for memory. I'm just using M. Dial M for memory. Murder, Hitchcock movie, you should watch. That's scary. And then watch what we do here now. M by S, M by RI, M by subjects by RI. Done. And how do we know what to test with what? Well, we just take a look and see what's below it that has subjects and the thing we're interested in it. So we want to find the effective retention interval. We're going to divide mean squared for retention interval by mean squared for subjects by retention interval. For memory test type, we're going to divide it by memory by subjects, and then for the interaction of memory by retention interval, we divide it by the mean squared for memory by subjects by retention interval. Putting things together in order like this is called Yates order. It's named after Frank Yates, one of the founders of analysis of variance. So in fact, you'll see a lot of times, not always, but a lot of times the outputs from things like SPSS come out in Yates order. They don't always. Sometimes they'll do all the main effects, then all the two-way interactions, the three-way interactions, etc. So not every SPATS package comes out like this, but I think SPSS actually does. I know SAS does. I think R does. So we're just going to test. We don't test subjects. That's not an interesting thing. We test retention interval, memory by retention interval with 3 different error terms. Okay? When I say we test with them, we divide the mean squared for that thing by the mean squared for the thing we test with. So again, mean squared for retention interval divided by mean squared for subjects by retention interval. Because you can see eventually when these things start to get big, there's going to be a lot of error terms, there's going to be a lot of terms in general, and knowing what to test with what is a little bit difficult. Now, it is possible in SPSS, if you really know what you're doing and follow the great video tutorials that I have with SPSS, to tell it which is a random factor, a fixed factor, and all this stuff, and then it will test properly. You still should double check. A lot of people make mistakes here, and software will do whatever you tell it to do, even if you tell it to do the wrong thing. And I do get reviews, when I review things for journals, maybe 1 in 10 times people have used the wrong error term for analysis of variance. They didn't know. Because their software did something. They didn't tell it properly. They'll just do what it's told. So, let's wrap this up. Repeated measures are used a lot. In psychology, in life sciences, I said in general, because think about it. We're interested in change over time a lot, be it learning, be it memory, whatever. Be it forgetting, just development. We're interested in how organisms change over time. It's just something we're interested in. So we're going to use that a lot. When you think of subjects as just another factor, albeit a random factor, you can actually easily figure out the error terms. So figuring out error terms and components of a model like this is putting the terms in what's called Yates order. If you do that, you're going to be fine. And much of the rest of the course, the next at least 2.5 weeks, will be taken up with me showing you different designs, and then we will work out the source of variation degrees of freedom tape. And it's all going to be, then you do this, then you do this, and you test this with this, and then you do this, and this, and this, and you test this with this. Until we start regression in like April, this is what we're doing. It's going to get mechanical, but you'll also find that with some practice, it actually becomes quite easy. But it's all about practice. Any questions I can answer there on this stuff? We'll talk about the upcoming test in a moment, but if you have any questions on that. But if you have any questions on this stuff. Okay?